All right, let's talk about something that's literally all around us, all the time. It's this invisible force, right? But it holds the power to do things that are, well, kind of mind-blowing. We're going to dive into the hidden world of waves, and trust me, you're going to be surprised by what they can really do.
Okay, so take a look at this. This isn't some sci-fi movie. What you're seeing here is a real medical procedure called lithotripsy. And those blue lines? Those are sound waves. They're being used to completely shatter painful kidney stones inside someone's body without making a single cut. I mean, it looks like something straight out of the future, but nope. This is real physics happening right now.
So that brings up a pretty big question, right? How on earth is that even possible? How can you perform what is basically surgery with just sound? Well, that's the big mystery we're going to solve together.
So let's get into it. How does this surgery with sound actually work?
Before we can get to all the cool, high-tech applications, we've actually got to go back to basics. We need to really understand the fundamental physics that makes all of this possible in the first place.
And that brings us to our first and maybe most important question. What is a wave, really?
Okay, so here's the key idea. A wave is a traveling disturbance that transmits energy. But here's the part you've got to remember. A wave moves energy, not stuff. Think about it like this. If you see a buoy out in the ocean and a wave rolls by, the buoy just bobs up and down, right? It doesn't get carried all the way to the shore. That's because the energy is what's traveling through the water, but the water itself is pretty much staying put.
Now, it turns out waves basically come in two main flavors, and it all depends on how they wiggle. First, you've got your transverse waves. These are the ones that go up and down. Then, you've got longitudinal waves, which kind of push and pull back and forth. Let's take a look at what that actually means. For a transverse wave, this is the perfect example. Imagine you're holding one end of a rope, and you just flick your wrist. You see that? The rope itself moves up and down, but that ripple, that little hump of energy, travels forward, all the way to the other end. That's a transverse wave, plain and simple.
And for the other kind, the longitudinal wave, the classic slinky is the best way to think about it. You push one end and you see that little bunch up, that compression, travel all the way down. It's a back and forth motion. And you know what? This is exactly how sound works. It's just squishing and unsquishing air molecules to get to your eardrum.
Okay, awesome. So we've got the basics down, what a wave is, and the two main types. Now, let's peel back another layer and look at what makes up a wave. Think of it as the anatomy of a wave. Turns out, you can describe pretty much any wave using just three key things. You've got amplitude, that's basically its power. You've got wavelength, which is its size. And you have frequency, which is all about its speed, or how often it comes by.
So amplitude is just how tall the wave is. Simple, right? When we're talking about sound, a bigger amplitude means a louder sound. It's literally like turning the volume knob up on your stereo. And frequency? That's just counting how many waves pass by in 1 second. For sound, a higher frequency means a higher pitch. Think a tiny whistle versus a deep bass drum.
And finally, wavelength. That's just the distance from the top of one wave to the top of the next one. But get this, and this is wild. The sound wavelengths that we humans can hear range from as small as 2 centimeters all the way up to 17 meters. That's longer than a school bus. It's just incredible what our ears can pick up.
Now, here's something that is absolutely crucial to understand. The speed of a wave totally depends on what it's traveling through, the medium. Just look at this. In air, sound zips along at about 330 meters per second. But the moment it hits our body, into soft tissue, it speeds up to over 1,500 meters per second. That's almost 5 times faster. And then when it hits bone, whoa, over 4,000. That's more than 12 times faster than in air. And this difference is the secret sauce for all kinds of medical imaging.
Okay, so we've got the physics down. Now for the fun part. Let's connect all these dots and see how we actually put these waves to work to do all that amazing stuff we talked about at the beginning.
So one of the coolest ways we use waves is something called echolocation. And yeah, it's pretty much exactly what it sounds like. You use echoes to locate things. You send out a sound wave. It bounces off something. And by listening to that echo, you can build a map of your surroundings.
And you know what's so cool about this? Nature totally perfected it first. I mean, bats, dolphins, whales, they've been using echolocation for millions of years to navigate and hunt. The sonar we use on submarines or the ultrasound machines in hospitals were basically just copying a trick that nature figured out a long, long time ago.
Okay, so how do we get from a whale finding a fish to a doctor finding a kidney stone? How does this same principle let us see inside the human body and then, destroy something in there?
Well, the secret is all about focusing. Think about a satellite dish. It uses a curved shape to gather up waves and concentrate them on a single point. Medical ultrasound works the exact same way. It uses a special curved tool to focus sound waves. It sends out these little pulses, and by listening to the focused echoes that bounce back from all your different organs and tissues, a computer can stitch together an incredibly detailed picture of what's happening inside you. And this, right here, this brings us right back to that incredible kidney stone procedure. Remember how we said amplitude is the wave's power? Well, imagine taking thousands, even millions of these tiny sound waves and focusing all of their energy, all of their amplitude onto one single tiny spot. You concentrate all that power, and suddenly you have enough force to literally shatter a stone into dust. It's incredible. No scalpels, no cuts, just pure physics.
But wait, it gets even cooler. Because waves can't just see where things are. They can actually see things moving.
And this is all thanks to a little something called the Doppler effect. And I promise, you already know exactly what this is. You've heard an ambulance go by, right? You hear that me-me-om sound? How the pitch is really high as it's coming at you and then it drops way down as it passes? That's the Doppler effect. The sound waves get all bunched up in high frequency on the way in and all stretched out in low frequency on the way out.
Now, in medicine, this is an absolute game changer. Doctors use this exact same principle. They send sound waves into your body, and they bounce off your red blood cells. By measuring that tiny shift in pitch, that tiny Doppler shift in the echo, they can tell exactly how fast your blood is flowing and in what direction. It's like having a tiny little speed gun to check the traffic in your arteries, helping them find blockages and check on your heart health.
So there you have it. From a simple ripple in a pond to shattering kidney stones. It's amazing how this one idea, this traveling disturbance, can let us see the invisible, navigate the oceans, and heal people in ways that seem like magic. It all comes back to that one core concept we started with. Waves transport energy, not matter. So I guess the only question left to ask is, what ideas will you put into motion today?